Okay. Hi everyone, my name is Zhao from Nanjing University, and today I'm gonna talk about quantum pseudorandom scrambler. And this is joint work with Chuhan and Fang from Portland State University, and Minglong and Penghui from Nanjing University and Hefei National Lab. Okay, let's begin. In complex theory and cryptography, pseudorandomness is a crucial concept. It refers to objects that appear truly random to adversaries who don't have unlimited computational resources. Typically, the true randomness is a uniform distribution over a very large set S, and the pseudorandomness involves some distribution over a smaller set T, which allows for efficient sampling. When considering the adversaries, we often model them as polynomial time randomized algorithms or quantum algorithms. If adversaries with bounded power cannot distinguish those two objects, we then say they're computationally indistinguishable. If adversaries with unlimited power cannot tell those two objects, we then say they're statistically indistinguishable. In cryptography, we care how to achieve computational indistinguishability rather than statistical indistinguishability for practical purposes. This is because we can assume every attacker or adversary in our real world has limited resources. In quantum cryptography, Zhi, Liu, and Song proposed two interesting pseudorandom objects. They are pseudorandom states and pseudorandom unitary operators, which are quantum analog of pseudorandom generators and pseudorandom functions in classical cryptography. Roughly speaking, pseudorandom states is a set of quantum states which are efficiently constructible and is computationally indistinguishable from a high-random state on n qubits. As for pseudorandom unitary operators, it is a set of unitary operators which is computationally indistinguishable from a high-random unitary applied on n qubits. More specifically, we say a polynomial time quantum algorithm G is a pseudorandom state generator, or PRSG, if the following holds. When given a key K as input, the algorithm G will output a state phi K, and phi K is computationally indistinguishable from a high-random state in the following sense. When we randomly sample a key K and produce the state phi K, we want phi K is indistinguishable from a high-random state psi for any polynomial quantum adversary A, even if we provide A with polynomial copy of the state. We call the state generated by a PRSG the pseudorandom states, or PRS. PRSGs exist assuming the existence of quantum secure pseudorandom functions. For example, we can design an algorithm G which uses pseudorandom functions to generate pseudorandom states. It first prepares all zero state and apply Hadamard gates on all qubits, and then it queries a pseudorandom function on its phase. We can query using both a complex phase or a binary phase. The complex phase version is proved to be a PRS in JLS 18. And they also conjecture the binary phase version remains a PRS, and this is later proved by BS 19. PRSGs are useful to develop novel primitives, for example, the quantum money scheme and the quantum bit commitment scheme. Also, PRSG attracts the attention of researchers in the field of quantum gravity theory as they model the black hole as a pseudorandom state. Another quantum pseudorandom object is the pseudorandom unitary operators, or PRU. PRU is a set of unitary operators. These unitary operators can be constructed in polynomial time if given the key as input. And we randomly sample a key K. The unitary UK is indistinguishable from high-random unitary if we give the adversary the oracle access to the unitary we sampled. PRU is an interesting primitive. It is a quantum analog of pseudorandom functions in classical cryptography. Thus, it is believed that PRU may hold significant potential for various applications in quantum computing and cryptography. Furthermore, PRUs are shown to exist even if one-way functions don't exist. This suggests a weaker assumption for quantum cryptography. However, how to construct the PRU remains an open problem today. Several candidates are provided in JLS 18, but there is no formal proof of their correctness for now. PRU is a much stronger primitive compared to PRSG, and there seems to be a huge gap between PRU and PRSG. A simple argument shows that applying PRU on arbitrary pure state phi results in a state which is indistinguishable from a high-random state. In other words, PRU maps an arbitrary pure state to PRS. However, the PRSG needs a fixed initial state and may fail if we use another state as the initial state. For example, in the constructions we mentioned before, the initial state is all 0 state. And it is also not clear how to transform an arbitrary pure state to a pseudorandom state. And this is a modest property of PRU. Since constructing a PRU remains open problem, and there seems to be a huge gap between PRU and PRSG, we naturally will ask a question: can we construct something to bridge the gap between PRU and PRSG? And our answer is yes. We propose the pseudorandom state scrambler, as it scrambles an arbitrary pure state to a pseudorandom state, and we think it serves as the first step towards bridging the gap between PRSG and PRU. So in this work, we first define the quantum pseudorandom state scrambler, or PRSS. The definition captures the property of scrambling an arbitrary pure state. Secondly, we gave an efficient construction of PRSS from quantum secure pseudorandom functions and quantum secure pseudorandom permutations. This construction is by simulating a new random walk we propose. We call it the parallel Kex walk. And we prove this random walk converges to a higher measure in polynomial time, which is an exponential speed up compared to the original one. Moreover, we find a surprising property of our construction, which we call a dispersion property. It says that the output state of our scrambler form an epsilon net on the unit sphere. We also show some novel applications of our PRSS, for example, compact quantum encryption and succinct quantum state commitment. Okay, let's begin with the definition. Let H be a Hilbert space of dimension 2 to the n, and lambda be a security parameter. We say a family of unitary operators Rk is a PRSS, or pseudorandom state scrambler, if the following holds. First, the key length is bounded by a polynomial in n and lambda. And second, for every Rk, there is a efficient implementation of it. And the third condition states that for any state phi, if we sample a random key and apply Rk on phi, the output state Rk phi is computationally indistinguishable from a hard random state, even if we gave the adversary polynomial many copies. This coincides with definition of PRSG. So by definition, we know if Rk is in PRSS, then for any pure state phi, Rk phi is a PRS. And if Rk is a PRU, then it is also a PRSS. By strengthening the pseudorandom condition in PRSS, we define random state scrambler. For random state scrambler, we require the output state is statistically indistinguishable from hard random state in multi-copy settings. That is, the trace distance between the state produced by our scrambler and the hard random state is negligible. And we don't require bounded key length and efficient implementation for RSS, since when we use random permutation and random function to implement an RSS. So how do we construct a PRSS? We will first construct an RSS Rk with random permutations and random functions, and we show for any pure state phi, Rk phi is statistically indistinguishable from hard random state. Then we will replace the random function and random permutation in RSS with quantum secure pseudorandom permutations and pseudorandom functions. Then we obtain Rk prime. The security of pseudorandom permutation and pseudorandom function ensures that Rk phi is computationally indistinguishable from Rk prime phi. Then by the triangle inequality, we know Rk prime phi is computationally indistinguishable from a hard random state. This establishes that Rk prime is a PRSS. So from now on, we mainly focus on how to construct an RSS and show its output state is statistically close to a hard random state. And our approach is that we first propose a novel random walk and show it produce a state in polynomial steps, and this state is statistically close to a hard random state. Then we will implement a quantum circuit to simulate such a random walk. Here we will explain how to construct an RSS for real Hilbert space for simplicity, and it is easy to extend the method to complex space using same idea. Okay, we start with the random walk, which scrambles a pure state. The random walk we will analyze is a parallel version of Kex walk. The original Kex walk on unit vector x first randomly select two distinct elements ij from all coordinates. And then it randomly sample angle theta and rotate the corresponding coordinates xi, xj by the angle theta. Kex walk was originally from a model for Boltzmann gas and is is extensively studied in mathematical physics. For example, it is proved by PS17 that it converges to the higher measure on the unit sphere in n times 2 to the n steps. Keck's work also found applications in quantum information theory. Some techniques used in improving the mixing time of Keck's work have played an important role in proving some unitary design results. However, for building pseudorandom objects in computational settings, as far as we know, our PRSS is the first one to employ Keck's work directly in the construction. Okay. We proposed the parallel version of Keck's work. We call it the parallel Keck's work. The parallel Keck's work first select the perfect matching of all coordinates, and we denote the perfect matching by P. So there are 2 to the n-1 pairs in P, and for each pair in P, it samples an independent angle and rotates the corresponding coordinates by the angle theta k. Intuitively, each step of parallel Keck's work can be viewed as taking 2 to the n-1 steps in the original Keck's work. Thus, we expect this random walk has an exponential speed up and converges in O(n) time. However, the pairs being rotated in a single step of the parallel Keck's work are distinct and thus not independent. So the results for the original Keck's work cannot be directly applied here. Fortunately, we can prove the following theorem. Let phi t be an arbitrary parallel Keck's work. Here, phi t denotes the vector after t steps parallel Keck's work. For t is large enough, for example, t equals 10 times lambda plus 1 times n. We can show the trace distance between any polynomial copy of phi t and Hall random state psi is negligible. This means phi t is statistically close to a Hall random state. Next, we explain how to implement such a random walk. The circuit we construct is denoted by k sigma f, which uses a random permutation sigma and random function f. Roughly speaking, the random permutation sigma is used to randomly partition the basis to 2 to the n-1 pairs, and the random function f is used to sample a random angle for each pair. K sigma f then rotates each pair by the corresponding angle. So if we sample t-independent random permutations and t-independent random functions, and let circuit t sequentially apply k sigma 1 fl1, k sigma 2 f2 until k sigma t ft, they will represent the t steps parallel Keck's walk. Thus, with proper parameters, the output state of C is statistically indistinguishable from Hall random state. This established that C is an RSS. Then by replacing the random permutations and random functions in C with pseudorandom permutation and pseudorandom functions, we obtain a construction for PRSS. So until now, we have defined the PRSS and RSS and have explained how to construct an RSS and a PRSS. Surprisingly, by deeply exploring the parallel Keck's work, we find an interesting property of our scramblers. We call it a dispersion property. We found that if we start at an arbitrary pure state on the unit sphere and we apply the parallel Keck's work for n steps, then the output state is supported on the whole unit sphere, and its distribution is close to Hall measure in total variation distance. As for our construction of RSS, we know it can be viewed as a discrete version of parallel Keck's work, since we sample the angles from a discrete distribution. We can prove the output state are spread all over the unit sphere, and they form an epsilon net on the unit sphere, and the distribution on the net is close to Hall measure in Westenstein distance. This property is not necessary by the definition of PRSS or RSS, or even for PRU. And also, this property is not possessed by a regular pseudorandom state. For example, the random phase state we have seen before, it is easy to see the amplitudes are equal for every coordinates. Thus, the random phase state are highly constructed and concentrate on small region of the sphere. They are only close to Hall measure in average. Thus, we think our scrambler is much powerful compared to PRSG because it has such a strong property. And this strong property also shows the optimism of finally establishing a PRU via our approach. Okay, last we discussed the connections between the existing PRSG variants and our PRSS. The first one is the scalable random state generators. It traces the number of qubit number n and security parameter lambda separately, it refers to an algorithm G which produces a pseudorandom state on n qubits, and the advantage is bounded by a negligible function of lambda. Since we already separate n and lambda in our definition, our PRSS implies the existence of scalable PRSGs straightforwardly. And the second one is pseudorandom function-like state generators. It refers to an algorithm G, which takes a key K and a classical string X as input and outputs a n-qubit state, phi kx. It satisfies the following pseudorandom property. When we choose Q string to query and receive Q quantum state, these Q quantum states are indistinguishable from Q independent hard random state. Here we consider the small domain version, that is n equal to log lambda. We can construct a small domain version by using our PRSs in a black box manner. For example, the key of the algorithm G is a very long key, which consists of 2 to the n short keys. Each of the short key can be used as a key for our PRSS. When receiving key and X, the algorithm G apply RKX on the state X. The indistinguishability holds since G uses independent keys for different X. And the last one is the work by AGKL23. They construct a set of unitary UK on n plus m qubits. They show that randomly selecting a UK and applying it on a n-qubit pure state psi appended with m zeros, this is indistinguishable from applying a hard random unitary on this state when m is polynomial in the security parameter. This is because the advantage is bounded by 2 to the minus m. In other words, they gave a construction which maps a n-qubit pure state to n plus m qubit PRS when m is polynomial in lambda. However, when m is small, for example 0, their construction may fail to scramble an n-qubit pure state to an n-qubit pseudorandom state. And they call their construction the pseudorandom isomer trees. As for our PRSS, it is able to scramble an n-qubit pure state to an n plus m qubit pseudorandom state for arbitrary n, even if m is small. This can be done by applying an n plus m qubits PRSS on psi appended with m zeros. Okay, let's give some final remarks and future directions. Of course, the big open problem is how to construct a PRU. A PRU we have introduced before is a set of unitaries which are computationally indistinguishable from a hard random unitary. And a property of it is that it's able to scramble an arbitrary pure state. In this work, we propose and construct the PRSS, which realize such a property of PRU. As for PRSG, it is only able to scramble a fixed initial state and is subsumed by our PRSS. Thus, we think our PRSS bridges the gap between PRU and PRSG. One may be confused by another object called approximity design. The major difference between T-design and PRU is that the adversary in the settings of T-design are bounded. They can only use or query the unitary at most T times. However, for PRU, the adversary can use the unitary for an unbounded polynomial time. The circuit complexity of T-design usually depends on T and usually a polynomial in T. But the complexity of PRU is independent of the number of query times. There are several future directions that might be interesting. The first one is the most interesting one. We wonder that if our scrambler a PRU, and the second one is that can we scramble a mixed state? And we also wonder if there is another applications. For example, some application make uses of the dispersion property we have introduced before. And can we simplify our construction? For example, make it more local to meet the requirements of near-term quantum devices. In other words, can we use some local random circuit to realize a PRSS? And this also might be helpful to improve the dependence on T in T-design. Okay, that's all I want to share. Here's my email in case you have any questions or ideas.